array. I just specify the index as this number, and it'll go down into memory. Can't go negative. So I can't go to lower memory, but I can go down the stack arbitrarily far until perhaps I segfault because I went too far down and I went off the end of memory. Okay? Sorry?
Can you get, is there like colon, like a range?
Oh, no, not that I know of. You'd have to do each one individually. You understand what we're doing? Okay. This is fundamental. This is just getting warmed up because it gets super complicated in a minute. All right. If I want to do, I don't know if I can cut and paste this. Let's try it. If I want to see a bunch of values in a range, and I'm lazy, I bet you PowerPoint stuck some weird version of a quote mark that's not actually the standard quote mark. See those curvy quotes? That's PowerPoint being helpful. Let's see, does that work? Okay. So what happened here? This is my command. So what did I do? I printed, for some reason, this constant string, which are 8 of these values. What are these values? By the way, oh, not yet, never mind. Okay, so what are these values? Let's see, this is a Python program. -C means the program is on the command line, not in a file. And then this is a Python print. And what does this do in Python? It prints a single byte, and it allows me with \x to specify it in hex. So I'm printing a byte that's AA, which is not ASCII, right? ASCII is a 7-bit code from 0 to 127. And this has the high bit set, so this is some unprintable character. I'm just setting a bunch of these because in all hacking books, we put AAAA everywhere for some reason. So look for special marker values. I could put anything I want. I don't want to put zeros because zeros are common all over the place. I want to put something I'm going to recognize when I hit it. So I put I'm printing out a bunch of these, 8 of these bytes. Then, what's this plus? Concatenate. And then I'm printing out the literal string %0.8x, comma. And I'm doing that 200 times. Remember multiplication in Python is concatenation with yourself. So all of this is running. It's in this $parent format, which means that the output of this command, which is actually this is what I'm sending as argv1, right? And format is waking up and taking this as argv1 and sending it to printf. What are these question marks? Those are my AAAAA things, right? They're not printable, so I'm just getting question marks. After that, with no spaces, because if I have a space, argv1 ends and argv2 begins, and I don't want to do that. And then I'm doing this, and what's this doing?
Getting out the data.
Yeah, it's causing it to, there's no parameter selector here. I'm just saying, show me the first, show me the second, show me the third. And so what I'm getting when argv1 is passed in, this is argv1, passed into printf, is it saying, well, print out this stuff, that's just a literal bunch of garbage, so I just regurgitate the garbage, that's fine. And then these are all %x's, so I have to render whatever values are on the stack into hex. So my output is, I'm just reading down the stack. 200 words, where a word is 4 bytes. I'm reading 200 words down the stack and printing them out in order. Now the reason that I put these AAAA things in is because I wanted to see if I could find myself down the stack. If I find myself, I mean, remember, argv1 is on the stack, isn't it? Where I mean the string itself. Because remember in the old days when we first started talking about how like parameters and all that, right? So main gonna have an activation frame, activation record. It's gonna have its frame pointer here, its return address, then argc, which is gonna be an integer. In this case, it's gonna be 2. And then argv, what's argv? It's a pointer to pointer to pointers. Where do those pointers live? I mean, I guess the C runtime could have put them into the data segment, but they don't. It's on the stack. So it's gonna be, argv is gonna be a pointer down on the stack to an array of pointers. And there'll be 2 of them, followed by a null. A null pointer, 4 bytes. And what are these 2 pointers?
Pointers to the RV.
Pointers to the strings themselves that are null terminated strings, right? Those will be on the stack as well. So, shoot, I want more whiteboard down here. This is part of the stack, so we're still talking about the stack. What's this argv0? It's gonna be ./format or something, right? With a null terminated. And then this is argv1, and what's that gonna be? Right? It's gonna be \xaa, \xaa, 8 of those, followed by %0.8x, comma. It's gonna be this really long string that was my argv1. Okay. If this is passed to printf, printf will look for its parameters on the stack and start dumping your stack values, and eventually it'll get all the way down to itself. You get it? It's a weird thing to think about. But if the string says to look at the stack, and you look far down the stack far enough, you'll see the string itself, that's the format string that's causing things to be printed out. So you can find your own self on the stack. That's only because the setup before printf is called puts argv1 on the stack below the activation frame for main, which is where the printf is being called from. If somehow it had put them up into the data segment somewhere else, we'd never find ourselves. But since we're lower down the stack, we can find ourselves. It's quiet in here. You follow me? Do those AAA things show up?
Yeah.
So we looked far down enough, we got to them, right? AAA. So there's 3 there, 4 there, and the last one's here. There's all 8 of them. And preceding that, you can see format right here, right? Isn't that format? That's a /dot. Yeah. And that says format. AT is right there, and there's an alternative. It's a little endian, so you have to read it backwards, but this is FOR. That's an M. And that's AT. Alternator. And then followed by the A's. Okay? Do you get why you're seeing yourself when you look far down the stack? All right. Why the heck do I care about seeing myself? It's going to prove critical in a minute. But you got to push that on your mental stack now for a second. Knowing that we can place anything we want, literally, on the stack, including, let's say, an address that we want to overwrite or something. We can replace anything we want on the stack, and then we can reference it. And we don't have to go, what's this value, by the way? I'm printing out the stack. That's argc, that's argv, that's np, right? So we can see all those values. There's the return address. We'd probably like to overwrite that with address of shellcode or something, let's say. Okay. So we can place anything on the stack. And what if we wanted to skip all this and just find this immediately? What would we do? Use a parameter selector to just directly go to that. So if we know it's down there, if we get the right parameter selector, we can just surgically grab just that value, not have to deal with all the garbage in between. which is something we're gonna be doing a little bit later today, is just knowing by trial and error, or with a calculation, figuring out a parameter selector that will grab the value that's out of argv1 by looking down the stack with the right parameter selector. Okay? Confused? It gets worse. All right. So that's where we're at. I guess this is just an illustration of what we just saw, which is that when you look at the stack, you're gonna see this, and there's argc, which we just saw, and the 2 pointers and a whole bunch of other stuff. You keep looking down far enough, and then you find argv0, the string, and then you start seeing the AAAA stuff. That's what we just looked at. Plus we looked even further down.
And so just a quick, what is the 0.8?
Oh yeah, so that, before when I was doing just %x comma, remember 0 printed out as just a 0? 0.8 means to 0 pad it to a size of 8, so 0 will format as 0, 0, 0, 0, 0, 0, 0, 0, you know, make it 8 wide no matter what, by 0, by doing leading zeros. That's the normal way we look at a hex value of a 32-bit word. That's just a printing nicety. What would happen if I put the A's after the 0.08 X's?
They'd be further down the stack.
Okay.
Just keep getting A's on and on, up every single stack up.
Yeah, so I'm saying, instead of putting them in the front, I'm gonna put them at the end, right? So I'm gonna put these A's after all of these. Am I gonna see them?
Oh wait, no, because you have to put in more %x's.
I'd have to put in more %x's,
No,
but
you have to be right on first.
But then that would push the A's further up the stack. So then I need more %x's, but that pushes them further away, and I'd never reach them. See what I'm saying? So I'm gonna have my A's over here. So I need more %x's. This is have to be a longer string to be able to reach them, but the more of these I put in, the further down it goes, and it's like the cat chasing its tail. You'd never reach them. It's not important for any reason, it's just other than understanding like the dynamics of how, and the longer you make this, of course, this stuff gets shifted to lower addresses, which is gonna, of course, drive you crazy when you're doing homework. Okay. How about this? Could we see the environment variables this way? I've never tried, but they are on stack. They're in fact way past this point. They're down here. But once again, the more %x's you put, the more this all gets shifted up in memory, or to lower addresses, but up the picture. And the further you have to reach. So it may not be, I don't think you can get to the environment for the same reason. You could never get to the A's after. All right.
Couldn't you use don't you have that trick where you can percent number sign or
Yes.
number and then?
You can get that way, and you could surgically parameter selectors to get further and further down that way. That would work, because then you're not growing this
Right.
string as you're searching deeper. All right. So what have we accomplished?
On that
Yeah.
previous slide, when you had, or I guess actually when you printed out what had it, when we saw it in our A's, which was in the middle, like in the
Mhm.
terminal. What were we seeing? We were seeing quite a bit past. I guess then were we just seeing a bunch of those 0x's? I guess. Like we saw the A's, and then.
Yeah, this is all %0.8x over and over and over. That's what's coming
Yeah.
after these A's.
So
That's why you're seeing the same
okay.
string over and over. It's all this stuff. Anything else? Okay. So what can we do so far? We can read the stack. This is a read-only attack right now. We can inject bites into the stack, because we're setting argv1 to whatever we want. I can put any value I want into the stack, and then I can see myself, so what, right? You search far enough down, you see yourself. If there's sensitive information on the stack, this could be a bad thing, passwords. But here's the real interesting part, which is also unfortunately quite complicated, is that printf has the %n flag. I'd never heard of %n before I looked at these attacks. Very few people have, and in fact some printf libraries disable %n now because no one uses it except for attacking vulnerable programs in the way. So let's go take a look at %n. So here's a program. Well, here's a program, and it's going to use %n. %n says to printf, whenever it sees a %n, it says the corresponding parameter that goes with the %n is the address of an integer. And you are, Mr. Printf, supposed to write into this integer the number of characters output thus far in the printf. Okay? So if you are doing a printf and you want to know, and you printed out a bunch of stuff, including some %ds and %x's, and you don't know how much stuff the printf has output so far, but you want to know because you were trying to make like a columnized output or something like that, you can find out, you can ask printf itself, how many characters have you output thus far? And the way you ask it is you do a %n, which doesn't cause anything to be printed on the screen. It just causes printf to set an integer that you've supplied a pointer to for printf and said, fill in this integer with how many characters you've done so far. All right? This is a way of you asking printf to set an integer for you, not printing anything on the screen, but just telling you how much has been output. So that you can then do a computation based on whatever printf tells you to decide if you want to like put out some spaces and tabs to make a columnized output, something like that. Okay? Very obscure. So in this demo, this is not a vulnerable program at all. I'm just demoing what %n does. If I print out 1, 2, 3, 4, 5, and then tell printf %n, which corresponds to this integer I that I've provided, what's I going to be set to by printf? 5, right? Because 5 things have been output. And then there's a space, so that's another one. The %n is not going to increment the number of characters output because %n doesn't output anything. It just sets a variable. Then there's a space, that should be a 6th character output. And then %n again now sets this other integer supposedly to 6. Now that I have I and j set to 5 and 6, I'm just outputting 5 characters output, then 6. That's what should happen. 5 characters output, then 6. Okay? Seems very weird and useless, and yet it's part of the standard printf. To conform to the standard, you have to support this. All right. Well, this is interesting because I can tell printf to write to memory. And if I can control the format string, I can stick some %n's in there and tell printf to write stuff to memory. And I can control how many characters have been output thus far, because I can just output as many characters as I want, and then give it an address to write to. Maybe I can output a bunch of characters and then create a big integer that's the address of my shellcode, and then write that wherever I want, like on top of the return address. And then when I return, I run my shellcode. Make sense? That's what we're going to do. It is not easy. It's not easy to get it right. Okay, so we're going to exploit %n. I've never tried this before. What happens if I just say format %n? I assume it's just going to blow up. What did format just try to do?
Try to write to the EDP, I think so.
That's right.
Save stack
That's
pointer.
right. And what is it?
0, 0, 0.
It's 0. So format, I told format %n, which means that this address on top of the stack is a pointer to an integer. and you should output whatever number of characters you printed so far. How many characters has it printed so far? 0. So it tried to write a 0 to the integer at address 0, and we know what happens when we write to address 0. It's segfaults. You're not allowed to write to address 0. Every machine I've ever seen has always made sure that if you try to write to the address 0, you blow up. Starting memory at 0 and making it writable is a great way to let programmers never figure out what's wrong with their program, right? You want it to blow up when the program tries to write to a null pointer, to a 0 pointer. So 0 should always be a proscribed address. Okay, so there. Yeah. What if how about if we try to write to the next one? Ooh. So that would be, how do I write to the next address on the stack? I've never done this, by the way. I'm just doing this for the first time in my life right now. $2? What was that? That was the return address. Huh, let's try to write to that. That actually might work. No. Come on. We tried to write a 0 to this address.
And then we tried to return.
Yeah, maybe it actually.
Try to return to the memory of that address.
Yeah.
Right.
That's why, and maybe it's protected.
Maybe it's protected. Anyway, we're just futzing around. We can do something intelligent in a minute, I promise. Anyway, okay. So get %n in your head. However many characters have been output, that value is going to be written to the address that's according to the parameter that corresponds to the %n, wherever we are. We could select the parameter, or we could just use whatever the next one is in order. All right. We can inject addresses. How? Well, we can inject anything we want. I was doing A here, but I could handcraft this to be